So we're going to begin chapter 5.4, and I want to go ahead and first speak about a couple of things before we continue. Um, this chapter is on graphing the rational function, graphing the rational function. And what I want to speak first about is the important subject of multiplicities, multiplicities for vertical asymptotes. And there's two scenarios here that we can look at. One is that if the vertical asymptote, let's take two types of graph. What's that? So if we were to put in a couple of vertical asymptotes on one of these here, let's say we had a vertical asymptote right here, or perhaps right here, we can have the graph coming in and approaching infinity on one side and negative infinity on the other side, or it might be approaching negative infinity on the left side and positive infinity on the right side, upwards. This is the case when the multiplicity factor of the vertical asymptote is odd. The graph will approach infinity from one side and negative infinity from the other. No, it's not necessarily the left hand or the right hand. It could approach negative infinity on the left side, or it could approach positive infinity on the right side. Um, but we will have to do a little test when we graph to determine which side is approaching negative infinity and which one is approaching positive infinity. So what we want to do now is to so these are anything like, say, x cubed or x minus 7 to the power 1, or x plus 5 to the power 7. Anything that has an odd factor for the vertical asymptote will cause the infinities to alternate. One would go to negative infinity, one would go to positive infinity. And then if we have a situation where both, let's say we had a vertical asymptote right here and a vertical asymptote right here, and the graph was approaching, both ends of the graph were approaching positive infinity, like this, or both ends were approaching negative infinity, this would be for even multiplicity factors, both ends would go to infinity or negative infinity, both ends. So anything that say negative x squared where the power is even, or x plus 7 squared, or x minus 3 to the fourth power, anything that has that power even will result in, for the vertical asymptote, will result in um, the graph headed in the same direction, either to positive or negative infinity. Now, I don't want you guys to confuse this with multiplicity, which we did in chapter 5.3. Multiplicity for x-intercept, and we called it that if we had an even power, then the graph would touch, let's use 3 here just for clarification, touch at x is equal to 3. And if the graph had an odd power, it would cross at x is equal to 0. Okay, if it had, say, x plus 7 to the power 1, it would cross at x is equal to negative 7. Or if it had, say, negative x squared, it would touch at x is equal to 0. So two different types of multiplicity we're talking about. One is for the vertical asymptote, and one is for the x-intercept. Now, I'm going to give you some steps for graphing, and we're going to follow these steps for the problems that I do as example steps for graphing. I've simplified these steps as, to the basics. One, factor if possible, then write the domain. Step 2, reduce to lowest terms. Step 3, find the x-intercept, determine if crosses or touches. And we do that from the multiplicity. And FYI, to find the x-intercept, for the rational function, set the numerator of the function equal to 0 and solve for x. And then find the y-intercept by setting x equal to 0. Find the vertical asymptotes. Use multiplicity to determine behavior on either side. Step 5, determine the horizontal asymptote or oblique asymptote. Remember, the graph can only have one. It wouldn't have both an oblique and a horizontal asymptote. Solve to find out if the graph intersects the horizontal asymptote or the oblique asymptote. We do this by set function equal to the oblique asymptote or horizontal asymptote. 6, find intervals where the graph is above or below the x-axis. You may need to test values. Okay. Your graph should be complete at this point. Check with calculator. So what we want to do here is go ahead and do an example. F of x is equal to x plus 2 over x into x plus 5. And I'm going to put an axis down here that we're going to graph on. Let's do that back. I don't like to have this. Okay, here we go. Okay, so this is a y-axis and an x-axis. And as fast as we find information, we're going to put it on our graph. So step 1 says to check to see if it can be factored and write the domain. Cannot be factored. Cannot be factored. The domain all x such that x cannot equal to 0 or negative 5. Okay. Step 2. This is already in the lowest terms. Step 3. The x-intercept. Remember, I told you to set the numerator of the function equal to 0, because if we set this function equal to 0, we're in reality setting the numerator equal to 0. So set x plus 2 equal to 0. So this gives x is equal to negative 2 is the x-intercept. We can go ahead and mark that point on our graph. Negative 2. For y-intercept, set x is equal to 0, so y is equal to 2 over 0, which this means that there's none or no y-intercepts. We can't divide by 0, so no y-intercept. Step 4, we consider the vertical asymptotes. So there's two vertical asymptotes, one at x. Remember, we said the denominator equal to 0. X is equal to 0, and x is equal to negative 5. And on both of these, because the multiplicity that created them is to the power 1, which is an odd power, both approach, okay, both have the graph approaching infinity from one side and negative infinity from the other. So we're going to go ahead and draw in these two asymptotes. We have an asymptote at negative 5 and one at 0. We can't really see this, but it's there, okay? So x is equal to negative 5 and x is equal to 0. Step 5 says to compute the horizontal asymptote. So since n is less than m here, the horizontal asymptote is y is equal to 0. That means that the x-axis is a horizontal asymptote. Now, it becomes a little strange at this point because we have to determine if the graph crosses the horizontal asymptote. And that's pretty obvious here because right here, x minus 2, we know the graph crosses. We know the graph crosses because the multiplicity that created it was to the power 1. So the graph is going to cross the horizontal asymptote at negative 2. Okay? If you wanted to do a calculation for that, you would take the whole function set it equal to the horizontal asymptote, and if we solve this, you get x is equal to negative 2. But there's no need to do that because we already know that it's going to cross and we know that the x-axis is a horizontal asymptote. So we've got a couple, if we look in the middle of this graph here, I'm going to draw one scenario. This graph can do this, okay? Or it can do this. Because it's going to alternate on either side of the two vertical asymptotes. So we need to find out, we're going to test a single point to find out where the graph is actually, um, the y value for the graph is actually located. So let's test any point here. Perhaps -1. Test, let's say -1 is right here. We're going to test -1 into the original function, and we see that y is equal to -1 plus 2 over -1 into -1 plus 5. And that gives us +1 over -4. Okay, +1 over -4. That means that when x is equal to -1, the y value is a negative value. So that part of the graph has to be here. So it means that this part of the graph, when x is equal to -1, has to come down this way. Okay, it can't go above the graph, so it has to come down, and that means that this part has to go up. That's enough for us to complete the graph because it's alternating. This is going to infinity, so this n has to go to -infinity. This is going to -infinity, so this n has to go to +infinity. So if we're writing intervals here, it's above from -infinity up to, this is -5. I'm sorry, above from -5 to -2, and from 0 to infinity. And then below, from -infinity up to -5, and from -2 to 0. I'm going to kind of highlight those in color so you can see them. This is the above part. Okay. And then the below part is that one and this one. And the last thing I'm going to do is go ahead and put this graph into the calculator and confirm that it's the correct graph. Okay. So let's go ahead and put that in our calculator. I'm going to use the fraction bar to make it easy for us. Fraction, and the top of this function is x plus 2. The denominator of the function is x into x plus 5. Uh, 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 uh. So if we want, you can draw in the asymptotes, but at this point, you can only see what's happening to the graph. You can see that the graph is approaching infinity here on the left and on the right. But this is the best graph that you're going to get for this. You can try zooming out on it, but it's not going to do a whole lot more for it. Okay. So you might get a better picture this way. Or you can try zooming in on it and see what you get. Let's try to zoom in on it. I'm sorry, I'm zooming the wrong way. Zoom out. So that doesn't really help much. The only thing I can suggest here is to play with the zoom in a little bit, and then adjust the graph so you can see what's happening towards the left of it. So in other words, give the window some more negative x values, perhaps -8, maybe -10, and see if that helps it, okay? There we go. Graph it. Okay, perfect. So that kind of gives us what we wanted. Remember, you have to be able to play around with your graphing calculator sometimes to see what's happening. I'm going to go ahead and put this graph into our notes. So you can see the picture of it, okay? Okay, so continuing with a second example, this function is f of x is equal to x squared over x squared minus x minus 6. And as usual, we're going to set up coordinates right there. That's too far out. It's okay. That's much better. So this is 6. And we're going to do a 6 steps. Step 1, factor. So f of x is equal to x squared over x plus 2, x minus 3. So the domain, all x cannot equal to -2 or positive 3. Already in lowest terms, x-intercept, set x squared equal to 0, so x is equal to 0, and the multiplicity here is even, so it touches. So we're going to go ahead and mark that point. Right there, the graph is going to touch. Y-intercept, y is equal to 0 over 0 minus 0 minus 6, so y is equal to 0. Step 4, the vertical asymptotes. So both of the multiplicities are x plus 2 to the power 1 and x minus 3 to the power 1. So these vertical asymptotes are x is equal to -2 and x is equal to positive 3. And graph will approach infinity from one side, negative infinity from the other. It's going to alternate, in other words. We can go ahead and join these two. Here is 2. Let's go ahead and sketch in that asymptote at x is equal to 2. I'm sorry, 3. So that's x is equal to 3. And x is equal to negative 2 is somewhere about here. Okay? So let's go ahead now and talk about horizontal asymptote. The power on the denominator is the same as the power on the numerator. N is equal to m. So y is equal to 1 over 1. So y is equal to 1. So there's a horizontal asymptote at y is equal to 1. This kind of helps us to complete the graph because um, a graph a graph can only intersect a horizontal asymptote once, and it has to touch here. I want you to see my reasoning. It has to touch here. If it were to turn up like a U, like this, it would intersect the horizontal asymptote twice, which is not possible. So we have to come downwards and put it like this instead. Now, that means that if this end is going to negative infinity, this end here would be going to positive infinity. And if this is going to negative infinity here, this end is going to positive infinity here. So the only thing left for us to do is to determine where the graph intersects the horizontal asymptote. So set x squared over x squared minus x minus 6 equal to the horizontal asymptote, which is 1, and solve it. Okay, I'm expecting that you guys can solve something like this. This gives x squared is equal to x squared minus x minus 6. So this results in x is equal to negative 6. So graph intersects horizontal asymptote at negative 6 and 1, which is, remember, this point here is negative 2. So negative 6 and 1, that's negative 6 and 1. So what's going to happen at this point is our graph is going to intersect at this point, negative 6 and 1, and continue on its way. Okay, so let's go ahead and write the intervals where the graph is above and below the x-axis. So it's above the x-axis right here and right here. So above would be from negative infinity up to, this is negative 2. This is positive 3. So above from negative infinity up to negative 2, and above from 3 to positive infinity. And then below, and notice the division because the graph touches here, so it will be from negative infinity up to 0, and then from 0, sorry, not negative infinity, from negative 2 to 0, from negative 2 to 0, and then from 0 to 3. In other words, this is above, and then the below part, this part here, we do it in two sections, right there and there. And last but not least, we want to put this graph into the calculator and check to see what's happening. So for y equals, you can edit or just redo the whole thing. Alpha y equals, enter. So alpha y equals, okay, to get the fraction bar, x squared over x squared minus x minus 6. And I'm going to do a zoom standard on it first. And that's not too bad. That's not too bad. We don't need to make any adjustments on this. So capture this. And let's go ahead and insert it into the graph. Okay, we're looking at example 3 now. Example 3. So this one is, the function here is f of x equals to x squared plus x minus 6 over x minus 3. As usual, we want to put a little graph here that we can work with. Step 1, factor. So f of x is equal to x plus 3, x minus 2 over x minus 3. That allows you to write the domain as x not equal to positive 3. Step 2, already in the lowest terms, we can't reduce this. Step 3, 2x intercepts. X is equal to negative 3 crosses, and x is equal to positive 2 crosses. So negative 3 and positive 2. Y-intercept. So substituting 0 in here, we have y is equal to 0 plus 0 minus 6 over 0 minus 3, which is equal to 2. So the graph has a y-intercept at 2. So we can also put that in right there too. Next, we want to figure out the asymptotes. So vertical asymptote at x minus 3, and it's going to graph will alternate negative infinity and positive infinity. Okay, so let's go ahead and join that asymptote. So we've got an asymptote like this. At x is equal to 3. So it is 3, 4. The vertical asymptote, step 5, will be the horizontal asymptote. So horizontal or oblique asymptote, notice that n is equal to m plus 1. So this has an oblique asymptote, no horizontal asymptote. So we have to use long division here to compute the asymptote. X squared plus x minus 6. So this is x plus 4. You can check it. This is x squared plus 3x because we change signs. That goes away. This is 4x, bring down to negative 6. So minus 4x plus 12. We're not concerned with the remainder. Okay, not concerned with the remainder at all. So the oblique asymptote y is equal to x plus 4. We can go ahead and graph that really quickly. So when x is equal to 0, y is equal to 4. When y is equal to 0, x is equal to negative 4. And we can graph in that. I hope you guys know how to graph a straight line, y equal to mx plus b. So this is y is equal to x plus 4. Okay, so to determine if this graph intersects the axis is a little bit of work because we would have to take the function set it equal to the asymptote, which is x plus 4. And then if we FOIL everything out, we would get x squared plus x minus 6 is equal to x squared plus x minus 12, which has no solution. So graph does not intersect oblique asymptote. So we're ready actually to sketch this graph because if it doesn't intersect the oblique asymptote, the only way it can go is like this. I don't like how that looks. So pass through here, alternate on this side, and then it can't go this part because it will intersect the oblique asymptote there. So it has to only outer part of the graph is that part. So we can write the regions where it's above or below. Above, from the picture on the graph, above x-axis, from negative 3 to negative 2, and from 3 to infinity, and below from negative infinity up to negative 3, and from 2 to 3. I'm going to highlight those in color so you can see them. Above is this part, and this part, and then below is this part and this part. And then I'm going to go ahead and put this into the calculator and check to see that my answer is correct. So y equals, clear this graph out, alpha y equal, and we're going to put in x squared plus x minus 6 over x minus 3. Graph it. And we can't see the top part of the graph, so we might want to zoom out a little bit. Zoom out. Okay, and then we want to go ahead and put in the oblique asymptote to see how it works. X plus 4. There you go. So let's go ahead and capture this and put it into our notes. Question 4. So f of x is equal to x squared plus 4x minus 32 over x squared minus 2x minus 8. So step 1, we factor everything. That allows us to write the domain that x cannot equal to -2 or 4. Okay, we're going to put in some axes over here so we can sketch the graph. Step 2, we reduce to the lowest terms, so f of x, the x minus 4 cancels out, so we have x plus 8 over x plus 2. And the x minus 4 that cancels out becomes a hole in the graph. The y value for that hole is y is equal to 4 plus 8 over 4 plus 2, substituting to get the y value, which is equal to 2. So there's a hole, literally a hole in the graph at 4 and 2, right there, a hole in the graph. Step 3, the x-intercept. From the numerator, x is equal to -8, it crosses. The y-intercept is 0 plus 8 over 0 plus 2, which is equal to 4. So we have an x-intercept at -8, crossing, and a y-intercept at 4. This hole right here is at FYI 4 and 2. Okay. For vertical asymptote, set the denominator equal to 0, so the vertical asymptote x is equal to -2. Negative and positive infinity alternate. So call this -2 and sketch in our graph. -2, and let's move on. The horizontal asymptote. The power on the numerator is the same as the power on the denominator, so y is equal to 1 over 1. So we have a horizontal asymptote at y is equal to 1 right here. We have to determine if the graph crosses, so we would set x plus 8, x plus 2 equal to 1. This has no solution. So graph does not intersect horizontal asymptote. By the way, we know there's a horizontal asymptote. There's no oblique asymptote. Uh, let's see. Can we sketch the graph now? So if the graph has to go through here and it doesn't intersect the axis, the only way that the graph can go is like this. It has to cross here at 4. It has to go through the hole and continue. It can't cross that horizontal asymptote. That means that this part of the graph has to be like this. So we didn't need to test any points. So above x-axis, you can see from negative infinity up to negative 8, from negative 2 to 4, and from 4 to infinity. And below, I'm going to highlight these in color in a second, from negative 8 to negative 2. So yellow for above. This part of the graph is above the x-axis, from negative infinity up to negative 8. From negative 2 to 4 is above the x-axis, and then from 4 to infinity, because there's a hole there, we have to jump over that hole. And then the blue part is below this piece. So FYI, let me just go ahead and mark in this one point here that I forgot, negative 8. And as usual, we want to go ahead and put this into the calculator and check it. Remember that the calculator will not show you a hole in the graph, okay? So we can just graph the simplified form of this. Which is x plus 8 over x plus 2. And we can go back to a normal zoom on this zoom standard and pretty much see our graph, okay? So I'm going to go ahead and capture this really quickly and put it into our notes.